Hello, in this video we'll be working through the Unit 5 review. Number 1, a particle is moving along the x-axis so that any time t greater than or equal to 0, its position is given by x of t equals t cubed minus 12t plus 5. What is the particle's initial position? The initial position is the starting position, or the position at time t equals 0. So the position at time 0 would be p of 0, which means we're substituting 0 in for t. And I wrote p of 0, but actually our position function is defined as x of t. So we'll call this x of 0. X of 0 is 0 minus 0 plus 5, or just 5. So the initial position of the particle is 5. We don't have units given here, so I'll just say 5. Part B, when is the particle at the origin? When is it at the particle? When is it at the origin is asking for what time? At what time? So we're trying to solve for t. What is the position at the origin? Well, when it's at the origin, its position is 0. By position, we mean the distance away from the origin. So when is the particle at the origin means at what time is the position equal to 0. So we're going to let x of t equal 0. And our x of t is t cubed minus 12t plus 5. So we're going to let that equal 0. And that doesn't look like something I can solve by hand. So let's use our calculator and enter our position equation. So we have our t cubed minus 12t plus 5. And I want to know where that is equal to 0. I'm just going to try a standard window, although we are told that t is greater than or equal to 0, so I do usually change my window so that I'm only working on my interval. So it looks like there are two different times when the particle has a position of 0. Let's find each of those. So the first one is when t is 0.423. And again, we don't have units, so I'll just leave the answer like that. And then the second one is at time 3.233. So those are the two times when the position is equal to 0, meaning the particle is at the origin. What is the average velocity over the time interval from 1 to 4? Well, average velocity is change in position, so p of 4 minus p of 1, over change in time, 4 minus 1. Since I have my position equation in y1, I can easily get p of 4 if I call up y1. So I have y1 of 4 minus, and then y1 of 1. And I'm going to divide that by 3, which is 9. So the average velocity is 9. Part D, at time t equals 4, is the speed of the particle increasing or decreasing? So since I have the position equation, I'm going to go ahead and just work with my equation. I need to know if my velocity and acceleration have the same sign when t is 4 or opposite signs when t is 4. So we know x of t, the position, is given by t cubed minus 12t plus 5. And then my velocity is going to be the x prime of t. That's 3t squared minus 12. And my acceleration would be x double prime of t, and that's just going to be 6t. So x prime of 4. Well, 4 squared is 16 times 3 is a lot bigger than 12, so I know this is positive. And then x double prime of 4 is 24, which is positive. And since the velocity and acceleration are both positive at time t equals 4, I know the speed is increasing. Part E, when does the particle change direction? There's a couple of ways I can go about finding this. I can just work with my position equation. If I want to know when the particle is changing direction, it's when my position changes from increasing to decreasing or decreasing to increasing. I find it a little bit easier to work with the velocity equation. So I'm going to clear out my position equation and enter my velocity equation instead. And that is 3t squared minus 12. So I'm looking to see where the velocity changes sign. And it looks like that happens at 2, but it might not be exactly 2. If I hit trace 2, enter, it is exactly 2. So this velocity graph passes through the point 2, 0. That would be when my particle changes direction. And since the velocity is changing from negative to positive, the particle is changing from left to right. So the particle changes direction at t equals 2, since velocity changes. We can simply say changes sign, that's all we need. And then part F, when is the particle moving to the left? Well, that would be when the velocity is negative. And I'm looking at my velocity graph, and I can see that velocity is negative until I get to 2. Remember, we're on a restricted domain. T has to be greater than or equal to 0. So moving left on the interval from 0 to 2. Now, why did I use a closed bracket around the 0 and an open around the 2? Well, if I were to zoom out, let's say x min negative 1, and then I cut the bottom off of the graph a little bit. So let's make our y min maybe negative 15. When t is 0, the velocity is negative. So the particle is moving left. But when t is 2, the velocity is 0, and 0 is not a negative number. So I'm including the 0, but not the 2, since those are the places where v of t is less than 0. Part G, find the total distance traveled over the time interval from 1 to 4. So we're going to split this interval into 2 sub-intervals, and we're going to split it where the particle changes direction. So we're going to find the distance from 1 to 2, and then we're going to find the distance from 2 to 4. Okay, so the distance from 1 to 2. The particle is moving left on that entire interval, except right at 2. So to find the distance traveled there, we just find the change in position. We want p of 2 minus p of 1. That gives us the change in position, and then when we take the absolute value, we're going to get the distance. Plus, and we'll do the same thing over here, on the interval from 2 to 4, to find the distance traveled, we want p of 4 minus p of 2. And then we'll take the absolute value so that we're only adding positive distances. If I don't use absolute value, then I'm computing net distance traveled, not total distance traveled. So I need my equation for p of t again. Let me enter that. X cubed minus 12x plus 5. And then we want, nope, not a fraction. We want p of 2 minus p of 1. Which is negative 5, but we're going to make that positive 5. And then p of 4 minus p of 2. And that's 32. 5 plus 32 is 37. So the total distance traveled is 37. Number 2, the table below provides the velocities of a rocket recorded at specific times. Part A, is there ever an interval during which velocity is 0? Well, at this time here, when t is 12, the velocity is 2. And then at time t equals 14, the velocity is negative 3. So assuming we have a continuous function, we can't get from a y value of 2 down to a y value of negative 3 without passing through 0. Okay, so we can use the intermediate value theorem to explain how we know the velocity will equal 0. But there are conditions that have to be checked in order to use the intermediate value theorem. And for the intermediate value theorem, we need two things. We need our function to be continuous on our closed interval, and we need the number we're trying to solve for, which in this case is 0, to be in between the y-coordinates of the endpoints. Okay, so is this function continuous? Well, it's not given in the problem. It doesn't tell us that this is a continuous function, and we only have certain values of t in our table. So for all we know, at t equals 13, there might be a discontinuity. So we don't know. So I'm going to say, assuming that v of t is continuous, because if we don't assume that, then we really don't know. The velocity might equal 0, it might not. So assuming that v of t is continuous on the interval from 12 to 14, and then since 2 is, actually no, I was about to say something untrue. Negative 3 is less than 0 is less than 2. So since that is true, the intermediate value theorem guarantees a value c such that v of c equals 0. Part B, during which time interval is the rocket's position decreasing? The position will be decreasing when the velocity is negative. So we have negative velocity on this interval from 14 to 25. But we know that somewhere between 12 and 14, the velocity reaches 0, so really the interval is wider than that. It would start before 14, but we don't have enough information to determine where exactly the velocity first starts to be negative. So based on the data that we have here, we do know that the position is decreasing on the interval from 14, and it doesn't first start decreasing at 14 because, it's got to pass through 0 and then all the numbers between 0 and negative 3, which is going to happen before 14. But we do know that the position will be decreasing at 14, and then it'll be decreasing all the way up to 25. And since the velocity is negative at 25, we can say it's decreasing there as well. So this might not be the only time interval where the position is decreasing, but it's true that it will be decreasing on this interval since v of t is less than 0. And again, we're assuming that we're working with a continuous function, but in the context of this problem, since we're talking about the velocity of a rocket, it makes sense that it would be continuous. Part C, find an approximation for the acceleration of the rocket at t equals 5. So acceleration is derivative of velocity. We want to estimate v prime of 5. So we do have 5 in the table, but this is v of 5, and we want to estimate v prime of 5. We're going to do that by choosing the closest two surrounding points and getting the average rate of change. So that would be 4 minus 9, I'm looking at the difference in my y values, over 8 minus 3, the difference in my x values. So negative 5 over 5, or negative 1. In my numerator, I have the change in velocity measured in feet per second. In my denominator, I have the change in time, which is measured in seconds. So we need feet per second over seconds, or feet per second squared. Find the rocket's average acceleration over the interval from 0 to 12. Show the work that supports your answer, including correct units of measure. Average acceleration is going to be the change in velocity over the change in time. So we need v of 12 minus v of 0 over 12 minus 0. And we can read these values right from the table. V of 12 is 2. V of 0 is 15, and then 12 minus 0 is 12. So we have negative 13 over 12. In my numerator, I have velocity, that's feet per second, and in my denominator, I have seconds, so feet per second, or feet per second squared. Part E is the speed of the particle increasing or decreasing at t equals 5. So at t equals 5, we have velocity equal to 6, which is positive. And the velocity is decreasing around this point. It's going from 9 to 6 to 4. So the velocity at time 5, so v, is positive and decreasing at t equals 5, which tells me my acceleration is negative. So my acceleration at 5 is negative. And since the velocity and acceleration have opposite signs, I know that the particle is slowing down. So we can say, therefore, speed is decreasing at t equals 5. Number 3. An object is at rest when the velocity is 0. So v of t equals 0. An object is moving left when the velocity is negative. V of t is less than 0. An object has constant velocity when the velocity is constant, which would mean the acceleration is 0. An object's position is increasing. If the position is increasing, that means the velocity is positive. An object's velocity is increasing. So if velocity is increasing, then acceleration is positive. An object's velocity is decreasing. Velocity decreasing means acceleration is negative. Number 4, a particle moves along the x-axis with velocity as shown in the graph below. The position x of t at time t equals 0 is 5. At t equals 0, is the particle moving left or right? Well, we're looking at the velocity graph, and at time 0, the velocity is positive 2. And since the velocity is positive, the particle is moving to the right. So right, since v of t is positive. When is the particle at rest? That happens when the velocity is 0. And the velocity is 0 at 9 and at 17. So t equals 9 and 17 since v of t equals 0. When does the particle change direction? That happens when the velocity changes sign. And on this graph, that only happens at 9. The velocity is positive until we get to 9, and then it's negative after that. So t equals 9 since v of t changes sign. When is the particle's speed the greatest? Well, speed is the absolute value of velocity. So the largest positive velocity on our graph occurs right here at 5. But we also have a negative velocity of -6. And since speed is the absolute value of velocity, then the -6, the absolute value of that becomes a +6, which is more than 5. So 6 is the highest speed, or the maximum speed reached by the particle, and that happens at time t equals 15. The question says, when is this particle speed the greatest? So when is referring to the time t equals 15, since speed equals 6. Remember, speed is always positive, so you're looking for the largest absolute value in your velocity. Part E, what is the acceleration of the particle when t is 1? So here's 1, t equals 1, and then we want the slope of the graph at this time. So I'm just going to use rise over run. Here I can go up 3 and then over 2. So the slope is 3 over 2, or 1.5. So acceleration 3 over 2, and we don't have units here, so we'll just leave it 3 over 2. When is the acceleration 0? That's when the slope of the velocity graph is 0, and that happens on this interval here from 2 to 6. At 2, the acceleration is undefined because we have a corner point there. And at 6, the acceleration is also undefined because we have a corner point there. Number 5, verify that the function satisfies the hypothesis of the mean value theorem on the given interval. Then find all numbers C that satisfy the conclusion of the mean value theorem. For part A, we're going to start by checking our conditions. The mean value theorem has 2 conditions. 1, the function has to be continuous on the closed interval, in this case from 0 to 3, and then it has to be differentiable on the open interval from 0 to 3. We're working with an exponential function, and exponential functions are continuous for all real numbers and differentiable for all real numbers, so we don't have a problem there. We just have to state that we've checked it. So f of x is continuous on the interval 0 to 3, the closed interval 0 to 3, and differentiable on the open interval from 0 to 3. It's actually differentiable on the closed interval as well, but we only need it to be differentiable on the open interval. Therefore, we know the mean value theorem applies. Okay, and so somewhere the derivative of f has to equal the average rate of change of f on this interval. So therefore, f prime of, I'm just going to say c, that's how we're used to seeing it in our theorem. Therefore, f prime of c has to equal f of 3 minus f of 0 over 3 minus 0 for some value c on the interval between 0 and 3. So let's start by finding f prime of x. F prime of x equals, when I take the derivative of e to the negative 2x, I have to use the chain rule. So it's e to the negative 2x times the derivative of negative 2x. So negative 2 e to the negative 2x. And then my average rate of change, the average rate of what was that? The average rate of change on the interval from 0 to 3. That's our f of 3 minus f of 0. So f of 3 is going to be e to the negative 6 minus f of 0 is going to be e to the 0, which is 1, over 3 minus 0, like so. So I'm just going to find this now on my calculator. So we have e to the negative 6 minus 1 divided by 3. Okay, so negative 0.3325. Somewhere my derivative is going to equal that value. So we set our derivative equal to that value and solve. I'm going to store that value as a, and then I'm going to solve this graphically. So I'll enter my derivative equation, negative 2 times e to the negative 2x in y1, and then I want that value, that average rate of change in y2, so I'm going to put a since I've stored that as a, or you can just type the number in there. And then let's look at the graph. I don't know if I have a good window. I can do a little better with the window. My y min and y max don't have to be so extreme. Maybe we'll just go from -1 to 1. And I'm only working on the interval from 0 to 3, so it's a good idea to limit your window to that interval as well, from 0 to 3. And I can see that I have one solution, so let's find that. And I get x equals 0.897. So that's the c value I was looking for. And it is between the endpoints 0 and 3. Part B, f of x equals x over x plus 2. We're working on the interval from 1 to 4. Well, x over x plus 2 is not continuous everywhere. It has a discontinuity at -2. However, -2 is not in my interval. And since -2 is the only discontinuity, I know this graph is continuous everywhere else. So I would say f of x is continuous on the closed interval from 1 to 4. Is it differentiable? Rational functions are going to be differentiable except where they're not continuous. But if you need to check that, if you're not sure about that, you can either find the derivative equation and see where it does exist, where it doesn't exist. So wherever the derivative doesn't exist, then f is not differentiable. Or since we are using a calculator here, we can graph that original equation. X over x plus 2. I'm working on the interval from 1 to 4, so let's adjust our window. I'm not sure what I need to do with y values, but it's probably not -1 to 1. Let's just go -10 to 10. And maybe -1 to 1 would have been better. Let me do -2 to 2. Okay, so there is our function f of x on the interval from 1 to 4. It is continuous and differentiable everywhere. I verified that on the graph. Everywhere on that interval, I should say. So f of x is continuous on the interval, closed interval from 1 to 4. And it is differentiable on the open interval 1 to 4. Therefore, the mean value theorem applies. Or I'll be more specific. Therefore, the mean value theorem guarantees a value c on my interval from 1 to 4 such that f prime of c is equal to f of 4 minus f of 1 over 4 minus 1. Let's find our derivative equation. So f prime of x, I'm going to use the quotient rule to take the derivative of x over x plus 2. Derivative of top is 1 times the bottom minus the top times the derivative of the bottom over bottom squared. And that would simplify to just 2 over the quantity x plus 2 squared. So we're going to set that equal to our average rate of change. We need to find our average rate of change. I have my function f of x in y1. So my average rate of change, I want y1 of 4 minus y1 of 1. and then I'm going to divide that by 3. 1/9. So somewhere I know my derivative is going to be equal to 1/9. We can solve this graphically. I'll enter my derivative equation. And let me tighten up that window. Okay, still not fantastic, but it works. I'm going to get that point of intersection. And I get 2.243. That is between 1 and 4, so that's the C value that I'm looking for. Number 6, for what values of A, M, and B does the function f of x satisfy the hypotheses of the mean value theorem? They're not really asking us to do anything with the theorem, they're just asking us to check the hypotheses of the mean value theorem, and there are 2 conditions that we need to check. 1, f has to be continuous on the closed interval 0 to 2, and 2, f has to be differentiable on the open interval from 0 to 2. We have a piecewise function, so if there are discontinuities, well, first of all, if we look at the equations of the pieces, 3, that's linear, it's also polynomial, so it's continuous and differentiable everywhere. Negative x squared plus 3x plus a, that's polynomial, so continuous and differentiable everywhere. And then mx plus b, that's linear, which is also polynomial, which is continuous and differentiable everywhere. So each piece independently is continuous and differentiable. However, when you have a piecewise defined function, wherever you split this into your different pieces, you potentially have a corner point or a cusp or something weird going on. So we have to check what's happening at 0, what's happening at 1, what's happening at 2, in order to figure out if our graph is, in fact, continuous this entire time. So starting with continuity, let's check continuity at our endpoints. In order for the graph to be continuous at an endpoint, all that we require is that it's defined at that endpoint. So f of 0 equals, well, when x is 0, f is 3. So we've got that. The other endpoint 2, when x is 2, so right here, when x is 2, f is m times x plus b. So x is 2, mx plus b becomes 2m plus b. 2m plus b. So that does exist. So we're continuous at our endpoints. The other place that could potentially be a problem is where the domain splits. So when x is 1, are we continuous at 1? It's not quite as easy to check continuity at 1, since it's not an endpoint. We require more than the function just be defined. Not only does it have to be defined at 1, so we will check, is it defined at 1? Where does x equal 1 exactly? That's the bottom piece, because we have less than or equal to symbol connected to the 1. So when x is 1 exactly, we're in the bottom piece, and x has a value of 1, making this m plus b. So f of 1 is defined, but we need more than that to be continuous. We need the limit as we approach 1 from the left to equal the limit as we approach 1 from the right, and that limit has to equal f of 1. So we have 3 things to check. 1, find the value of f of 1, which we did, m plus b. 2, find the limit of f as x approaches 1. Now, we need to check the limit from both sides. So we're going to find the limit from the left and the limit from the right. Limit from the left. Numbers to the left of 1 are in the second piece. And we're going to evaluate that limit using substitution. So I'm looking at this second piece and I'm letting x equal 1. That gives me negative 1 plus 3 plus a. To find the limit as x approaches 1 from the right. Numbers to the right of 1 are larger than 1, so now we're in this bottom piece. And I'm using substitution, so I'm going to let x equal 1. I get m plus b. So in order for the limit of f as x approaches 1 to exist, negative 1 plus 3 plus a has to equal m plus b. And I see we can simplify this more. Negative 1 plus 3 is 2. So 2 plus a would have to equal m plus b. That has to be true. So 2 plus a equals m plus b. If that's not true, then our graph is not continuous. And we're trying to find values that make our graph continuous. So we're going to come back to this later, but we know this has to be true. And then for continuity, the third thing you check is that the limit is equal to f of 1. So we already have that set up as well. Because f of 1 is m plus b. Our limit is either 2 plus a or m plus b. We can say it either way. They're both equal to each other. So setting them equal to each other just, again, gives us 2 plus a equals m plus b. So that has to be true in order for f to be continuous on our closed interval from 0 to 2. The other part of the mean value theorem, the other condition, is that our function is differentiable on the open interval 0 to 2. Now, in order to be differentiable, we need the limit of the derivative to be the same as we approach 1 from both sides. We don't have to worry about endpoints because the theorem doesn't require differentiability at the endpoint. So I don't have to check anything about 0 and 2. I just have to check what's going on at 1. So I need to come up with my derivative equation. F prime of x equals, the derivative of 3 is 0. The derivative of negative x squared is negative 2x. The derivative of 3x is 3. The derivative of a is 0 since a is a constant. The derivative of mx plus b is m. So there's my derivative equation for each of my pieces when x is 0, when x is between 0 and 1, and then the closed interval from 1 to 2. So we need to know what is the limit of f prime of x as x approaches 1. And since 1 is where our domain splits, we have to check this from the left and the right. The limit of f prime as x approaches 1 from the left, I'm looking at the middle piece. I'm letting x equal 1. I get negative 2 plus 3, which is just 1. If I evaluate the limit of f prime as x approaches 1 from the right, I'm in the bottom piece, I just get m. And these two, in order to be differentiable, these two limits have to equal each other. So 1 must equal m. Well, that's nice. Now I know the value of m, and I can substitute that in over here. So I have 2 plus a equals 1 plus b. But I still have two unknowns, so I either have to figure out what is A or what is B. If we go back to our original function, in order to be continuous, then if f of 0 is 3, then when I go just a little bit past 0, I should be coming from 3 as well. Or in other words, if I check the limit as I approach 0 from both sides, I should be getting the same value there. So the limit as we approach 0 from the left is 3. The limit as we approach 0 from the right, let me write that out, limit of f of x as x approaches 0 from the left is just 3. We substitute 0 in for x, but there's no x, so we just get 3. Then the limit of f as x approaches 0 from the right, I'm going to substitute 0 into this middle piece here, which gives me 0 plus 0 plus a. And in order to be continuous at 0, these two have to be equal to each other. So that tells me that a is 3. And then if a is 3, then 5 equals 1 plus b, and b equals 4. So I have a equals 3, b equals 4, and m equals 1. Number 7, a trucker handed in a ticket at a toll booth showing that in 2 hours she'd covered 159 miles on a toll road with speed limit 65 miles per hour. The trucker was cited for speeding. Why? Justify your answer using the mean value theorem. We can calculate her average rate of change, or her average speed on this trip. We know that she traveled 159 miles in 2 hours, and the average rate of change is just going to be her change in position, which is 159 miles, over the change in time, which is 2 hours. So the units here would be miles per hour. And if it had been 160 over 2, that's easy. That's 80 miles per hour. So this is just under 80 miles per hour, or 79.5. Okay. So 79.5 miles per hour was her average rate of change, or her average speed. So the mean value theorem would guarantee that at some point between 0 and 2 hours, her average rate of change was equal to her instantaneous rate of change. So she must have been driving 79.5 miles per hour at some point in those 2 hours, which is well over the speed limit. Now, in order to use the mean value theorem, we are, of course, making some assumptions. We're assuming that the function, her position function, is continuous on that interval and differentiable, but that seems like a reasonable assumption to make. Number 8, let f be a function that is continuous on the closed interval -1 to 4. The function f is twice differentiable except at x equals 1, and f and its derivatives have the properties indicated in the table below, where d and e indicates that the derivatives of f do not exist at x equals 1. For x between -1 and 4, find all values of x where f has a relative extreme point. For each of these values, determine whether it's a max or min. Justify your answer. So we can use f prime of x to help us figure this out. We know that wherever f prime shows a sign change, f is going to have a relative extreme point. So the derivative starts out negative, which tells me that f is decreasing. And in between -1 and 0, the derivative is negative. So f is decreasing. At 0, the derivative is -1, still negative, so still decreasing. Between 0 and 1, derivative is still negative, so f is still decreasing. It's decreasing this entire time until we get to 1, where the derivative doesn't exist. After 1, in between 1 and 2, the derivative is positive, telling me that f is increasing. So the f does change from decreasing to increasing, but since the derivative doesn't exist at 1, it may or may not be a minimum point. It depends why the derivative doesn't exist. Does the derivative not exist because there's an asymptote? Well, there can't be an asymptote because f is defined at 1. f of 1 is -1. There's a point there. Is it non-existent because there's a discontinuity? Well, we were told that the function was continuous, so that's not the reason. So that tells me that the reason the derivative doesn't exist must be because of a corner point or a cusp. And a corner point or cusp still does count as a relative max or min. So it looks like we have a relative minimum at x equals 1. Okay, so I'm going to say relative min at x equals 1, since f prime changes from negative to positive. And then continuing on, so from 2 to 4, the derivative is positive, which means f continues to increase. So that is my only relative extreme point, just at x equals -1. Part B, for x between -1 and 4, find the maximum value of f. Maximum value is referring to the y coordinate. What is the highest point on the graph, the highest y value on our graph? So we can look at the row for f of x. It starts out at 1, and then it's decreasing, goes down to 0, still decreasing, goes down to -1. Then it turns and starts increasing up to 0, and then by the end, it has increased up to 3. So 3 is our maximum y value. The way we find an absolute maximum is to find the relative maximum. So we already know there's a relative maximum when x is 1, and then we evaluate the function at that point. So f of 1 equals -1. Then we compare that to the endpoint values. That was our only relative extreme point. If we had others, we would test the others as well. So now we look at our endpoints. The endpoints are -1 and 4, and we find the y coordinates at each of our endpoints. So at -1, f is 1, and at 4, f is 3. Now from this list of values, we choose the largest one. That's our absolute maximum value. Part C, on the axes provided, sketch the graph of a function that has all the characteristics of f. So there are a few points that we know for sure where they belong. When x is -1, f is 1. So that point is on our graph. And then we have 0, 0, 1, -1, 2, 0, and 4, 3. Now the rest of this, it's sort of up to you how you want to draw it, as long as you make the function correctly increasing or decreasing and then correctly concave up or concave down. So between -1 and 0, first derivative negative, second derivative positive. That means f is decreasing concave up, decreasing concave up. Between and at, let's see, at 0, the slope is -1. Okay, that's a little tricky. So the slope, like the tangent line has to be kind of like that at that point. Between -1 and 1, no, between 0 and 1, between 0 and 1, first derivative is negative, second derivative is negative, the function is negative. So below the x-axis, decreasing, concave down. Below the x-axis, decreasing, concave down. And I'm not sure I really achieved my slope of -1 at 0, but it's reasonably close, I would say. At 1, we know our derivative is undefined, so I'm going to make it look like there's a cusp right there. Between 1 and 2, negative, positive, negative. So below the x-axis, increasing, concave down. And then what's happening at 2, the derivative has to be 1. So I'm already off a little bit. Let's try that again. The slope has to be kind of like that. So this is difficult. Again, I'm not sure I really achieved a slope of 1 there, but fairly close. Then between 2 and 4, positive, positive, positive. So above the x-axis, increasing, concave up. Increasing, concave up. Oh, I got a little wobbly there. Concave up. So something like that. Again, if I had done this perfectly, the slope right here would be 1, and the slope right here would be -1.